Today, we're going to be looking at absolute convergence, which is when we're looking at the absolute value of the series. We're going to be looking at conditionally convergence. So this is when there's a disparity between the absolute convergence and the stuff. And then we're going to look at how to check for other methods, like other tests for absolute convergence, which includes the ratio test and the root test. So I think it's going to be a nice and quick video. So let's hop right into it. Okay. So first of all, what is absolute convergence? Or how does a series converge absolutely? Well, what we're looking at here is when a series is converging when we look at the absolute value. So if we had an alternate series that was, let's say, minus 1/2, and then plus 1/2 squared, then minus 1/2 cubed, that kind of stuff. When we look at the absolute value of this, what is this going to look like? It's going to be 1/2 plus 1/2 squared plus 1/3, 1/2 cubed. So it's just going to all be pluses. And that's what absolute convergence is. We're looking at the absolute value of that series. So let's look at this question really quick. It asks, is the series converging? Absolutely. Is it absolutely converging? So we have the equation minus 1 to the n over 2 to the n. And this would give us, actually I write it down here, this by itself would give us minus 1/2 plus 1/4 minus 1/8, right? But when we take the absolute value of that, we take the absolute values of these, what that's going to give us with is 1/2 plus 1/4 plus 1/8. So it's no different than 1/2 to the power of n. Yeah, no different from 1/2 to the power of n, right? And that's the magic of the absolute, is because it removes the minus, and it's just basically 1 to the n over 2 to the n, which is right down here, 1 to the n, 2 to the n, which it's going to look like this. And what we realize is that it's actually a geometric series. So a geometric series with a ratio of 1/2, right? It's just 1/2, the ratio is 1/2 here, this is ratio, and it's just two different powers. And if the ratio is less than 1, the absolute value of the ratio is less than 1, the series converges. So this series right here absolutely converges. And what does that tell us? When something is absolutely converges, then its normal series is also convergent. So if this is convergent, if the absolute series of this is convergent, then the normal one is convergent too. That's kind of the magic with absolute convergence, is that if you can find convergence with the absolutes, then the normal series will be convergent as well. So let's look at another example for absolute convergence. We have sine of n squared over n squared, right? And we need to see if this is convergent or not. Well, one thing we realize is that because sine is like this, if you were to take its absolute value, it's going to look something like this. And this value is always going to be between 0 and 1, right? 0 and 1. Sine of theta, the absolute value of that, is always going to be smaller or equal to 1. And what you can do is you can set up a comparison system where we can do probably direct comparison tests. So let's see how we do this. We know that because sine of theta is less than or equal to 1, if we take n squared over both sides, that's also going to stay true. And so we have is this situation here, and we know that 1 over n squared through the integral test, right? The improper integral of this from 1 to infinity is convergent, because 1 over x to the p, if p is larger than 1, then it is convergent. And so by the integral test, we know that 1 over n squared is convergent. And by direct comparison, right, direct comparison test, the sine equation is also convergent, because a larger one, if you have a larger one that's convergent, then the smaller one must also converge as well. So that's how you test it. Sorry. That's how we can tell that sine n squared over n squared is absolutely convergent. And if sine n squared over n squared is absolutely convergent, then the actual series itself, like if this is convergent, then the normal series is also convergent. So which is really useful. A quick note that if a series is not absolutely convergent, that does not mean that it's divergent, right? You can have a series that is not absolutely convergent, but still be convergent normally. So keep that in mind. It's just like the other test. Just because it's not absolutely convergent does not mean that it's convergent. Okay, let's keep going. So now we have a situation where we would define as conditionally convergence. Conditional convergence. Why would I write about that? Conditional convergence. So conditional convergence is when the series itself is converging, right? The series itself is converging, but the absolute series does not converge. So let's do a question here where we show that the this series right here is conditionally convergent. So let's test for its normal convergence. This is a alternating series, right? It's 1 over ln 1 minus 1 over ln 1 plus 1 over ln 2 minus 1 over ln 3. So it's an alternating series. So what we can do is do the alternating series test. That's the first thing we should do. The limit of this series, okay, it's equal to 0. That's the first thing. And then we need to check if it's a decreasing series, which means the next term should be smaller than the preceding term. So we have n plus 1 here and the nth term here. So minus 1 to the n plus 1 and minus 1 to the n, that's the same size because it's just going to be 1 or minus 1. And then you have ln of n plus 1 and ln of n, right? Ln of n plus 1 gives you a bigger number. This one's a smaller number. You have a bigger denominator, then the number is smaller overall. A smaller denominator, the number is bigger overall. And so therefore, it is a decreasing series, and so it is normally convergent through the AST test, through the alternating series test. Okay, now let's show that it is not absolutely convergent, which means it's absolutely divergent. So let's take the absolute value of this, right? So if it's minus, so initially it was minus 1 ln 1 plus 1 ln 2 minus 1 ln 3, that kind of stuff. But then now let's look at when we absolute value these, that's going to be 1 ln 1 plus 1 ln 2 plus 1 ln 3. So it's really simple. It's just 1 over ln n. That's the kind of idea when we do absolute values. The minus 1 just turns into 1 to the n. And what you end up with is we can compare some stuff, right? We see 1 over ln n. That means we want to do some kind of thing to it, preferably where we have a form 1 over xp next to it. So we do ln n is like smaller than or larger than xp, and then we do 1 over that. So let's do ln n is smaller than n. That's true, right? Because if we have 100 as n, then ln n is the same as e to the x equals 100. What's the x? That's probably like 5 or something. I don't know. But the ln n is going to be smaller than n itself. And when you take 1 over that, 1 over a smaller number is a bigger number. And 1 over a bigger number is a smaller number. And so the signs flip. And what you end up with is you have another situation for the direct comparison test. You know that 1 over n because like it's x to the p, 1 over x to the p, and this p is smaller than or equal to 1, then it's divergent. So now we know that that's divergent by direct comparison test. We know that the absolute series is divergent, so it's absolutely divergent. And then therefore, and because it's absolutely divergent, we don't, like, it doesn't mean that it's normally divergent. In fact, we found that it's normally divergent. So it shows that just because it doesn't absolutely converge, doesn't mean it can't converge normally. And so then we say this series here is conditionally divergent. Okay, let's do a few more. There's a few more tests that we need to know for absolute convergence, something called the ratio test. So we can do these two. It's something called the ratio test plus the root test, and I'll show you what the root test is later. But the ratio, basically, these stem from the idea of geometric sequences. So if you have a alternating series that functions almost like a geometric sequence, then we can just find one where the r is less than 1, and then we know that it's convergent, right? So it's a similar idea to that. So suppose that you have a series that behaves like a geometric series. So you'll see it's like almost like a common ratio, and then it's multiplied by something to power, right? Okay, and so therefore, the next term is almost like the nth term multiplied by a common ratio gives you the next term. And it's here. So it's some kind of multiplier, aka common ratio, and we call that L, right? And so the convergence of the series depends on L. Does that make sense? It's just like R, right? Okay. So now the ratio test says that assume L, and this is the ratio that we were talking about. And the way you find this ratio is that you take the limit from n to infinity of an plus 1 over an. This is just the multiplication between the two. If you think about like an plus 1 equals LAN, what you're doing is L equals an plus 1 over an, right? Simple algebra. You just do the limit of that to infinity to find the more general one when n is big enough. So then you have, if L is larger than 1, then the sum of an is absolutely convergent. So remember, it's like 1/2, 1/3, 4/5, anything less than 1 If the ratio is less than 1, then it's convergent. If the ratio is larger than 1, then it's divergent, just like geometric sequence. And then when L is equal to 1, that gives us no information, and then we have to use a different test. So I know it's a bit different from geometric sequences, where if R equals 1, then you know it's divergent. But this is not true. If L equals 1, that's because the form is not a geometric sequence. Like the form isn't 1/2 plus 1/2 squared plus 1/2 third. This is, if you get 1, it's because the form isn't like this, right? Okay, so there's also something else called the root test, where L is the limit from n to infinity of the nth root of the absolute value of an. So this is actually doing the same thing as this. This is also finding the ratio. You just use it in a different circumstance, where, like, for example, you have 1/2 to the power of n, for example. Then if you do the nth root of this, it just eats away the n, right? So that's the circumstance we'll do this, but it's a similar idea. It's the same L as before, and the same rules. If L is larger than 1, if L is smaller than 1, that's getting smaller over time, so it's converging. L is larger than 1, that's diverging. And if L is 1, there's no info, you got to do a different test. So we got a few examples here to run through. So let's try this. So we have this equation here. So it's -1 to the n minus 1, n to the 3 over 3n. So you can see how we have n to the 3 over 3n. And if we were to have, let's say, 3n plus 1 over, if we had n plus 1 over 3n plus 1. Well, 3n plus 1 is just 3 to the n times by 3, right? You can see how these kind of cancel out. So I think we should use the ratio test, where we can put one on top of the other and cancel things out. That's the kind of circumstances you want to use that for. So let's take the absolute value of this is n cubed over 3n, because the -1's turning into a 1 to the n. So 1 to the n is just 1. You're not changing the equation. You can treat it almost as if it's just this. 3n cubed over 3n. And then if you do an plus 1 over an, what you end up with is n plus 1 cubed over n, 3n plus 1, n cubed over 3n. And then you just do some transformations with it. Take this one up, take this one into here. And what you end up is here. You can cancel out the 3n and the 3 to the n, right? Because that's just 3n times 3. So what you end up with is just 1/3. You take this 3 out, and that's 1/3. And then you end up with something like this. That's just this cubed. And then you can do this. And so the lim to infinity, I think I write here, lim to infinity is 1/3 multiplied by 1 plus 1 over n. That to infinity is 0. So it's 1 plus 0, just 1. Cubed is 1. And then that's going to be 1 times 1/3. It's just 1/3. And so the limit exists, right? So first of all, L exists, and L is less than 1. So therefore, it absolutely converges. Okay, so let's look at another example here. Let alpha be any number, and then you have any number to the power of n over n factorial. So I put an extra segue into here, and I was just saying we could try doing a divergence test to this if you guys want to try doing a divergence test. So basically, lim of alpha to the n over n plus n factorial, what is that equal to? Well, basically, when we do this, when we're trying to find which one's growing faster, is an growing faster or is n factorial growing faster? If the denominator grows faster than the numerator, the limit exists and it turns to 0, right? So that's the idea. So what we're saying is when we have n plus 1, we think of the next term. What you basically have is alpha n. So alpha n plus 1 is just equal to this, alpha n times alpha. Same thing for factorial n plus 1. So it's just factorial, like this right here, this factorial, n plus 1 factorial is the same thing as n plus 1 multiplied by n factorial. And so it's easy to see that n plus 1, when you increase by 1 for every n plus 1, the numerator is growing by some constant. It could be 100, it could be 100,000, it could very well be -2, right? But the bottom is growing by infinity plus 1 every time. And so basically what we end up with is the bottom's growing really fast, and so it's going to tend to 0, and the limit is 0. But then that doesn't really help us, because if the divergence test gives us 0, then that we have to use some other info. But that's just a quick idea. So again, it's the same idea here. You set up for them to be above each other, and they cancel out really well. You get something like this. Go back to here. You get something like this, and then again, limit n to infinity, that's infinity 1 over infinity 0, a times 0 is 0. So limit is 0, which is less than 1, and therefore it is absolutely convergent. L is less than 1. Okay. So this is another situation, but this is with the root test. So you can see how it's all to the power of n. So let's try out the root test here. The root test is you want the absolute value of the sequence and then the square root of n over. So basically that's just 1 over n on the outside. The n's cancel out. You end up with this. And we want to find the limit to infinity. You just multiply it by 1, right? 1 over n over 1 over n is just 1. So we're not really changing the function, just making it easier to work with. It's 4 plus 1 over n over 7 minus 1 over n. You do the limit to infinity of that. These turn into 0. And then you get 4 over 7. And because the L is less than 1, then it's absolutely converting. So it's the same idea. I don't know if I have the time for this because I have to go really quick. Okay, just one last thing. I want to revise the continuous function theorem really quick. So let's look for a few examples when L is equal to 1. And let me tell you, and really quick remind you that when L equals 1, it's usually because it's not in the form of a geometric sequence. So it's not in the form of 1 1/2 plus 1/2 squared plus 1/2 cubed. It's just not in that form. So that's why it turns out like this. But let's see. So the sequence of 1 over n, let's do the root test of that. So the root test of this would give us root of that. So it's 1 over n to the power of 1 over n. How do we do this? We use the continuous function theorem. So what you do is you take the ln like this. You take the ln of the limit. You take the ln of this, the whole ln. You see that? You see how this whole function goes in? You take the ln of that. And therefore, because ln is a continuous function, we can take the limit out of the ln, right? The limit goes out of the ln, and that's where it is right now. The limit's outside the ln, and the ln's here. And it's the ln of 1 over n to the power of 1 over n. 1 over n can pop out here, and you can see that's where it goes. And therefore, now, n to infinity is ln of 0, which is ln of 0, which is 1, but technically also 1 over n. 1 over n, that's going to turn into 0, right? Because 1 over infinity is 0, so it's 0. And therefore, remember that on the left side, we still have limit of this. Now we can take the limit out. We can take the limit out of the ln and then do e to the power of the whole sequence, whole like expression to remove the ln on the left side. And then we have 0 here, so we do e to the 0, and that's 1. So the limit of this whole thing is 1. L equals 1, and that's no info, right? Just because it's not the same thing. And this is for 1 over n squared. Again, there's no reason to do the whole thing again because we have 1 over n squared over 1 over n. We do that. And then if you do the root n, or not the root n, but you can take the 2 out, or actually it's 1 over 2n, that's my bad. But again, it goes to 0, it goes over e to the 0, it's 1 again. So L is going to be the same 1, right? And the idea is that 1 over n, right? 1 over n, we know this is divergent. But then 1 over n squared, 1 over n squared, we know this is convergent. But then they both got L equals 1. And so that's the idea. If you get L equals 1, it tells you nothing. And I just want to give you a key takeaway here is that if a series is, for example, if a series is something to the power of n or something to the power of any factor of n, then you should use the root test because then you do the root of n that removes the n. And when the series is like a fraction or something that you can cancel, then you should use the ratio test. But yeah, that's it. Thank you guys for watching my video. You guys have a good rest of your day.